So from 0, 4, imagine we're following this. You kind of draw your graph down more, following the arrows. Where are the arrows now? Uh-oh. Something like that? That's pretty horrible, huh? Well, let's say we want to be a little bit more systematic with this idea. Yeah?
When do you know how when you merge the constants? When do you know when not to merge it?
The integrating, the last part of the integral, the last integral that you do basically, is the one where you don't want to get rid of the constant. Okay, well let's take a look at. That was a bad picture. That's not a very good picture either. So let's go back to this point and let's see if we can find a more systematic way of I'm trying to get the 4. There we go. See if we could find a more systematic way of tracing out this graph. Because sometimes we're interested in some numerical value of the solution. Maybe we don't necessarily care about what the solution is, but let's say we had our differential equation, which was dy dx plus y is equal to x, and then we had our initial condition, y of 0 is equal to 4. And we may or may not care about this function, but what we might care about is what this is equal to, and maybe at 2. So what we could try to do is find a numerical approach to this by following the tangent lines, more or less. Okay? And we do have a slope field, and this is defined the way this is defined. We actually have our tangent lines, or we should be able to get our tangent lines, right? So if we take our differential equation and write it in, I don't know what this is called anymore, normal form or something, standard form, where you have the derivative by itself, that's essentially the slope, and that slope is equal to this thing. So what we could do is we can make a line at the point 0, 4, right? So what do we need for an equation of a line? 2 points, or if we have a slope, we just need a slope and a point, right? So we have a point, we just need the slope at that point. We could find the slope at that point, right? What's the slope at that point? What? -4. So m is equal to, well, the derivative is just the slope, but we have to evaluate it at a particular point. So when x is equal to 0 and when y is equal to 4, we have the slope. So that would be -4. Right? 0 minus 4. You guys with me? So if I were to draw a line, what is the equation of that line? We have a slope, we have a point 0.04, and we have a slope of -4. What's the equation of your line? Y minus y equals -4x plus 4. Does this look weird? Y equals, where do these numbers come from? I just made them up, huh? It's the point slope formula. I just solved for y by itself without simplifying. You know, you guys are into that y equals mx plus b business. I prefer this one. So if we were to catch that line from here, we would see this line going down this way with a -4 slope. Now, obviously, that's not a good approximation, but maybe if we take that and go as far as, I don't know, 0.5, when x is equal to 0.5, maybe we'll follow this line just so far until we get x is equal to 0.5, and then from there, maybe we should try another slope. Does that idea make sense so far? 0.5 might be a little too far. But for the sake of trying to visualize this, you can't see anymore. It's too close. Let's say we go down this far. Okay? So what if now I'm interested in this point right here? So I know that's 0.5. What's my y equal to here? Oh, I didn't write down the line. Let me write down the line. What was the line again? Y is equal to 4 plus -4 x minus 0. So, what if I go to that point? What do I want that point to be? What should my y value be? I'm kind of out in the middle of nowhere. I took my tangent line and I stretched it out, follow it all the way down until I have the next value of 0.5. Where do I end up? What's my y value? How did you get 2? Plug it into, so the equation of this line, right? So this is this line right here. When x is equal to 0.5, you plug that in here, y evaluated at 0.5, and then 2 is what you guys said, right? Because you plugged it in here. Or is it because you saw it in the graph? It's 0.5 comma 2. It's right here. That's where we ended up. Okay? Anyway, so now we got a new point. So y is equal to 2. So we had 1 point, 0 comma 4. Now we have 0.5 comma 2. So what if I take it from here now and then see what my tangent line is if I follow that tangent line for another 0.5 steps? So I need the slope, right? I have a point, I need a slope. M for my new m here is equal to, according to this, it's x minus y. So x minus y dy dx. X is equal to 0.5. Y is equal to 2. Negative 1.5? Negative 2, negative 1.5, right? So it's not going to be as steep as negative 4. It'll look like it'll come out this way more. So this equation of this line is y is equal to what? Write it the way I wrote it earlier. Y equals to 2 plus the slope, negative 1.5, times x minus 0.5. Right? Okay. So that line was y equals to, what was it again? 2 plus minus 1.5 times x minus 0.5. Now I'm going over here. That looks confusing. What if we look at it this way? Where does this end up? X is equal to 1, y is equal to 1.25. Okay? So now we're going to take it from this point and then find another graph, another line to go ahead and do that. So, do you see the problem here, though? What's the problem? Did you guys get an answer for this, by the way? Who thinks they did it correctly? I'll just copy your answer. Anybody do it correctly?
I left this one like constant. I don't know. I modified it.
Oh, man. I don't know.
Just check mine. I want to know mine. This is kind of like the concept of steps.
Steps? Kind of. Well, I could do one more, but do you guys get the idea here? Now, I'm taking steps of 0.5 here. It's not very accurate. So what I wanted to do is I wanted to graph the actual answer. Y equals 5 times e to the negative x
and then
plus x minus 1. Oh, 5e to the negative x, that looks like a transient term, right? As it goes off to infinity, it goes to 0. So look how far we are. We're way off. By the time you get to x is equal to 1, we're over here. And we wanted x is equal to 2. Maybe we should do this a couple more times just to see how off we are. But that's too much work. So do you see what's happening? If we were to try to follow along, we got that. Let's see if I can draw it in our scratch work over here. Oh, I'm out of space already. Oh, let's keep going. We might as well just do it. Sorry. Indecisive. So in order to get to figure out, we know that x is equal to 1 at this point, right? We're going to move another 0.5 units. So x is equal to 1. Now the question is, what's your y value? And we found the y value by putting it into the last equation of the last line. So let's take that equation of that last line and put 1 in for x. So y is equal to 2 plus negative 1.5 times 1 minus 0.5. And what's this equal to? What is it? Somebody punch it. What is it? 1.2. Oh, that was the answer, right? It was here already. Oh, I took it out. .25. So now we have that. We'll follow it along. And make a new slope. M is equal to x minus y minus, or x minus 1.25. That's just 0.25 negative. And then you make the new equation. Y is equal to 1.25 plus negative 0.25 x minus 1. So we need to do this like a couple more times to get those values. Okay. So let's draw this. We got y minus 1.25 plus negative 0.25 times x minus 1. And then we want this from 1 to 1.5. And maybe we change the color to something that we can see a little bit better. So it looks like it's going to start to bounce back up, but it went down way too low. And then we do one more and we'll be going. It looks like we'll have a positive slope after that. Okay? All right. So this actually is called Euler's method. So this is Euler's method of approximating your solution numerically. So let's see if we can get a quick briefing on Euler's method. As we saw in that example, the steps that we're taking are kind of important. And when we do take those steps, the larger the step, the more we're going to go off tangent from the curve that we're following, right? You know, sometimes if you go off on tangents, you're just kind of way off. So, but if you do a small step, that tangent, how much you're off by, is only a little bit, and then that'll kind of keep you closer to the graph in general. So here's an initial value problem. It's written this way, where you got the slope, or the derivative, is equal to itself, and then on the right-hand side would just be a combination of your independent and dependent variables. And then you have an initial condition, x naught, y naught, as your point. Now this is that linearization business. Where you have the y value plus the slope times x minus x naught. So that was studied in great detail in Calc 1 when we talk about linearization. And so it turns out that your slope, your y prime evaluated at x, is actually the f function, the whole right-hand side of your differential equation. And then your y value is just y naught. So it turns out that those steps that you're taking come into play right here, where you have x minus x naught. I don't know if they call it step. Yeah, small step. It's a step. And it turns out that the smaller that is, the more accurate your equations are going to be. And what that's going to do is that's going to bring you to the next point from your x naught, y naught. It's going to give you your y1. Your x1 is kind of predetermined because you know the steps already. But this will bring you to y1. And then if you want y2, you do the same recursive process where you're calling on y1 to figure out what the next step is. And so, without doing the math for that, I'll have you just look at the book to do the math for that. Here's our magic formula for Euler's method. And what you want to do is basically keep track of x naught and y naught are some fixed numbers. You find x1. Well, x1, x2, x3, all that are predetermined because you just add h to it. You add h to the x's to get to the next step, and then you end up where you need to end up. But your corresponding y values is what's really important. So this is y naught. This is given. That's part of your initial condition. But everything else you have to get from the formula. So what we could do is we can find these things, and then if we happen to know the answer to the differential equation, like the actual function, we can compare our answers, and that's what we're going to do. But in general, the reason why you're using this is because you can't solve for your differential equation analytically, so you want to just find numerical values, and you do that by finding close approximations. All right? So we did our example here taking steps of 0.5. We didn't quite finish it. But what I'm going to do is this is kind of tedious to do by hand. So I'm going to use technology. I'm going to use two things today. One is a seemingly non-mathematical program that we all have access to. Yeah? Pardon me? Oh yeah, I think so. Because it's just a matter of copying things. And then the more interesting part is looking at the solution to it. So, all right. So I'm going to use. Actually, I should have just used Google Sheets. Huh? I'm not going to use anything fancy in Excel. I'm just going to use its functions capabilities for this. So let's start off with our x values and our y approximations. And I think I had starting off with 0, and I took a step of 0.5. And then I want to go all the way up to 2. So my first initial value is 4. And to get to my next step, I needed, well, let's take a look at that formula again. What's that formula look like? To get to the next step, I need the previous y value times h, which is our step size, times the function evaluated at this. What? All right. Let's try to remember our function again. I forgot our function. Okay, what's our function? Our function is dy dx. And that is equal to, uh-oh, did I just freeze? Dy dx is equal to, oh, yeah, it's equal to, because I want dy dx by itself, is equal to x minus y. And then we have y of 0 is equal to 4. So that's our problem. And then let's copy this formula here. The formula is y sub n plus 1 is equal to y sub n plus the h times the function, which is x minus y. But it's the function evaluated at not just the random x, but the previous x and the previous y. Okay, so with Excel, it's kind of neat because I could just type in one formula and then click and drag. Have you guys ever done that in Excel? That's really cool. So I'm going to say that this is equal to y, which is the previous y, plus h, which is 0.5, times the f function. So what's the f function? It's x minus y. It's the previous x, so that's the 0, minus the previous y, which is 4. And then it's 2. That's what we got, right? So here's the magic. You click on that and drag it down, you get 1.5, which is our next answer. And then you do that again. We didn't get this far, but our final answer should be 1.3125. Pretty cool, huh? The actual solution to this, again, Elliot, y is equal to x plus 1. Did I do that right? Minus 1. So if I were going to do that, since we know the actual function, we have the what do you call it? Liberty? No, we have the advantage of being able to compare the actual answer. So if we want to see the actual answer, it's 5 times e, which is exp in most other cases, to the negative x, and the x is for this one is 0. Plus x minus, oops, I don't want just x, I want to actually use this x minus 1. So it's not surprising that your first one should be exactly the same, right? But if we take a look at the others, it may or may not be the same. In this case, it's a little bit off. Okay? All right, so we know that a step of 0.5 is not a good step. So now let's take a smaller step. Now that we have this computational machine working for us, let's see if we could take smaller steps. So let's do another one here. And this time, let's take steps of 0.1. Or should we do 0.25 first to make it look all drama and stuff? Oh, we could just do 0.1. Because now we have the answers we can compare. And so, and we want to get all the way to 2. So I think we'll need 20 of them or something. Yeah, this might be a little too much. But we'll see. All right, so this is our step. So these are our values. We're going to have lots of values. And now let's find the approximation using Euler's method. So according to Euler's method, this should be exactly the same as my previous command, right, except for the h is different. So it's going to be the previous y plus the h, which now is 0.1, and then the x minus y. So I'll click on the previous x minus the previous y. And then these are all my values. Let's compare it to the actual. So before, with those big steps, I ended up with 1.31 compared to 1.67. Way off. Well, considerably speaking. I'm pretty off over there. But now I got 1.60 compared to 1.67. A lot closer. So you would imagine if you do this more times, you would actually see the big difference, or to see that it's going to get closer and closer. Okay? Does that look interesting? So the other part of this is to try to graph it. Let's see if we can graph this. See, I don't know if I can graph two of them at the same time. So I want to do a scatter plot that's connected with dots. So the approximation is in blue, and then the other one is in red. Now let's compare that to my first attempt. So this is my first attempt, which is kind of off. You see the distances between those two graphs are a lot bigger than the distances between these two graphs. Okay? And to really compare them numerically, since we are doing this numerically, to do the comparison, we can actually just subtract the approximation versus the actual value, since we have the actual value. So let's take a look at an error here. And for the first one, we're not going to get an error because, well, it's exactly the same, so the error is going to be 0. But if you take a look at the rest of them, you'll see the error progressively get larger. 0.5, 0.58. Well, this one actually got smaller. But in general, it gets larger. Let's take a look at the error here. So the error is 6/10 or 7/10 compared to an error here of 3/10. Actually, 7/100 is what I meant to say. So smaller error. Okay. All right. Another tool. Let's see. Let me take some pictures of this, and I'll take pictures later and put it in our notes. But another tool that might be useful would be Matlab. How many people have access to Matlab? Okay. So if you have access to Matlab, that's great. If you don't have access to Matlab, there's an equivalent program called FreeMat. And actually, there's several equivalent programs that run kind of like Matlab. And this one is called FreeMat. And so it's kind of complicated to use unless you just want to add. That's easy. But if you want to do something like we're doing, it takes a little bit more instruction and stuff like that. So let's and MATLAB really depends on vectors and matrices. MAT stands for matrix. It's a matrix laboratory. It's a matrix lab, and so that's how they got the name. So let's see if we can do this using MATLAB. Should I do it? Okay. Let me walk through it using MATLAB. And what we're going to do is we're going to want to define a function first. So let's define a function. And the way, so this is syntax stuff that you'll probably have to look up. And so the way we're going to define a function is like this. We'll call it f. So f is the name of the function. And then this is a function of two variables that will have x and y. So that's the first part. And then another space here will tell you the actual function. So the actual function that we've been dealing with is is x minus y. Okay? Now, if you just press enter in MATLAB or FreeMat, you'll get your output, and they'll tell you, in this case, they'll just echo that you meant to say that you have a function, and this is how the function looks like. If you don't want the output to come out, like if your output is going to be some long output, then you can use a semicolon to not have the output. All right. So let's identify our initial points. Our x naught was equal to, what was our x naught again? 0. And, oh, so it's echoing my information. So y naught is equal to 4. Now, if I don't want to see this echoed back to me, I'll just put a semicolon, and then you'll see that it's not going to tell me what my last input and output was. Of course, if you have this set up, you can see it on the side anyways. Y naught was equal to 4, x naught is equal to 0. F is an annotated function. So all that information about your variables are stored off to the side here. You can take a peek and see what you have. All right, our H. Should probably do the 0.1, right? We got a good approximation with 0.1. So let's put 0.1 for H. And a good thing to know is when you should end. And so we want our x, your final x value, let's call it xf for final, to be 2. I think we want it to go up to 2. Okay? So in Excel, what I did after I figured out what my h was, I just kind of listed my x values, right? So let's see. Your x list. So this is one way to make vectors in Matlab. So x is equal to, if I go from x naught with a step of h and the x final, I'm going to get a long vector that looks like this. 0, 0.1, 0.2, 0.3, 0.5, etc. Okay? So that's my x list. And it turns out that you can see this a little bit better if it was vertically listed, right? Because right now this is like a long lengthwise vector. But if we see it vertically listed, this kind of looks like my output for my Excel file. The at just says that you're going to define a function. So this is MATLAB is a numerical computational thing. And so when you start doing abstract functions, like when we say x squared, just saying x squared is technically an abstract function. And so for a program like MATLAB to deal with it, you have to define it that way with the at symbol. And then I could define g of x is equal to x squared by just saying g is equal to, now this is my symbol, and then I only have one variable, and then I'll say x squared. And so when I say g of 2, what's g of 2? G of 2 is equal to 4. No, because g is equal to x squared is all symbols. Actually, x is already something, so that's not going to be technically symbols. But when you do something like this, it's not going to work out properly. All right. We have a list now. We need to define our y values. So in MATLAB, we're defining our y values to define y values, we need to have a certain list of things. And so what we're going to do first is, I think here it says we have to allocate space for your y values. So one way to allocate space for the y values is say y is equal to, oh, we need the length. How long is this? How many numbers are in here? 20? So y is equal to I just put a whole bunch of ones in there. I guess it didn't matter what I put in there. So y is now a list of ones, and I'm going to start defining. I suppose I should have said y, the first one, is equal to 4, isn't it? Oops. Oops. Oh. There it goes. So let's change the first element to a 4, and then we'll work the rest of them out. So this is going to involve some programming. So I'm going to throw in a for loop here. I couldn't find any simpler way of doing this. So sorry if you're not a programmer. So I'm going to do a for loop. What was the length again? 20? So what I'm going to do is I'm going to assign y values from the previous y values. So this is my for loop. This is the beginning of my for loop, and I press enter, and I didn't get an output. That's because Matlab knows that I'm in the middle of something here, a for loop. It's waiting for the actual stuff inside the for loop. So inside of the for loop, I want my y values. So my I starts off with 1, and so I want to assign y of 2, my next one. And so I'm going to say y of 2 is going to equal to my previous y value plus my step, I think I call that h, and then my f function. Well, I'll just call that my f function. Let's call it f, because I defined f, right? I mean, I know what it is. It's x minus y, but I'll just use the definition of my f function since I defined it. And my x is my previous x value. Uh-oh, I don't know if this is going to work now. I hope so. And then my previous y value. And then I'll end it here. Didn't work. What? Let's take a look at y. Oh, looks like it worked. Did it work? So the question is, are these the same values that we got? 3.6, 3.25, 6, 3.25. I didn't reach 2. I only got to 1.57. Bummer. Let's take a look at the table and see if it'll come up. Oops. Whoops. I think I'm 1 short. So x is a 1 by 21. Y is a 20 by 1. So it's not matching. Let's see if that'll work out. I think it's 1.60. Let's just say that. Now let's take a look at x and y. Yeah. All right, now we got it to match. So you can see the table just like what we had. Actually, that last value here isn't quite accurate because I just made it up. But you can see how they kind of matched up. And then with this, I think you can plot it. Plot x prime. I'm using prime for Matlab is transpose. So instead of a 21 by 1 row vector, it becomes a 1 by 21 column vector. So just so it'll match up. Let's plot this. And then there's some weird, other weird options for Matlab. Having an O here says you're going to have O's for the actual points, and then it's going to connect the lines. And let's see if this will work out. Okay. Oh yeah, that's not good. Control C. Stop. Quit. Yeah, I need brackets for that. What if I just close it up? Okay. All right, let's try that again. This time with brackets. So by the way, if you press up arrow, it'll give you to the previous command, and if you keep pressing up arrow, it'll keep popping up to the previous command. So here's your graph. Okay. So why am I showing you all this? It's your new worksheet. So worksheet number 2, you actually have to either download Matlab or download FreeMat for free, or use Matlab. And then the things that I was doing wasn't quite exactly what's on this worksheet, but it is very similar to what I've just been doing. You'll get instructions. It has the web page where you can download FreeMat. It has all the steps that you can follow to create your plots and your solutions. And what you could do is you can literally just copy and then paste this onto a script, if that makes sense to you as a Matlab person, and then run it through in your machine so you can see how it runs. And then I want you to actually solve for these using Euler's method. Okay? So, good luck with that. And this will, I noticed that I didn't give you homework assignments for this. So the only practice you'll get in doing this is through this worksheet. And I probably won't give you a test. I probably won't test you on this. But I might test you on some of the theory behind it. Speaking of test,
What?
our first exam is a week from Thursday. See ya.